And the first paper will be DeepTAM, Deep Tracking and Mapping, and it will be presented by Huizhong from University of Freiburg, and Benjamin Ummenhofer, also from University of Freiburg.
Okay, thank you for the introduction. Benjamin and I will present our work, DeepTAM, Deep Tracking and Mapping. So DeepTAM is a dense camera tracking and mapping system which uses deep learning. It takes a video sequence as input and outputs a depth map of the keyframe and always tracks the pose of the camera. So there are many related works which estimate depths and poses with deep learning. Some just use single image, and there's also the case with two view, for instance, Demon, but this is only limited to 2 images. And here we want our system to deal with video sequences and compute camera pose for every frame and estimate the depth map for the keyframe. And we really want to combine classic methods and deep learning as much as possible. So, there are many methods that can do depth estimation and pose tracking, and why do we want DeepTAM? And instead of asking why DeepTAM, maybe we can first ask 2 following questions. Why not pure deep learning, and why not classic methods? So we all know that deep learning has a lot of advantages, but it also has a big problem that it doesn't generalize that very well. For example, here, so we train a network only on indoor data sets and we test on outdoor data. And you can tell that the single image network completely fails, while ours still generalize well. And here is another example on Kitty. So we didn't do any fine-tuning on our approach, and we take another visual odometry network that's only trained on Kitty. And you can tell that if a car moves forward, both method works well. But if you reverse the sequence, and our approach, DeepTAM, can give a reasonable backward motion, while the other method continues going forward. This is one big problem of, they only train on KT and they clearly overfit on the forward motion. But you can also see that generalization is not a big problem for classic methods, and why not we just take the classic methods? And now it comes to another big advantage of our approach, which is robustness. So here's an example that we show DTAM and also SGM, and you can see that they don't give a good estimate in homogeneous region, but our method can actually still give a robust estimate even when there is missing measurements. Here's another example that our approach is very robust to pose noise. And as you can see that here, with increasing noise, classic method really suffers a lot, but our approach still is able to get the main structure of the scenes. And this robustness is very important, not only because that it makes the system very unlikely to fail, but also it makes the initialization much easier. So for classic method, usually you need some special initialization, but here in our approach, actually we can start from just a constant plane, and after very few frames, the depth will converge to a good depth estimate, and the depth and pose will then improve each other. So I think now the question why DeepTAM is well answered, and because that we combine the advantages of deep learning and also classic methods, and in this way we can get a very robust and accurate system, and which also generalizes very well. Yeah, and now let's take a look at how can we achieve this. So this is how our tracking and mapping interacts with each other. Actually, they depend on each other. So tracking needs the depth map from mapping part, and mapping also needs the tracked camera poses. So now Benjamin will give a detail of the tracking part.
Yeah, I will explain the tracking part. So our tracking system is keyframe based. So we have a keyframe, which is a color image and a depth map. And now we want to find out what are the relative poses of the other images relative to this keyframe. Here we have now a keyframe, and we have the current camera frame. And what we want is we want to know how are they related to each other. What is the relative pose? And the naive way of training now a convolutional neural network to do this is we just take these two images as input and apply the relative pose ground truth as a training signal. The disadvantage of this is it doesn't work very well. So this problem is quite difficult. So one reason for this is we want to have true 6 degrees of freedom pose tracking, and the space is quite huge, as you can see here. And because the space is so huge, we can get images like this. So the left image here is the keyframe, the right image here is the current camera image. And as you can see, these images are visually not very close to each other, and it's quite difficult to establish correspondences between these two. So to solve this problem now, we generate a virtual keyframe. So we take the depth map and the color image and render a new virtual frame that should be close to the current camera frame. We adopted this from classical methods, so there are many that use this, for instance, DeepTAM. So now the problem is much easier to learn. As you can see, the virtual frame and the current camera frame, they are visually quite close, and the image space or the space of the poses is much smaller, because we only have to predict now this small pose increment, which you see here as a red arrow. Another big advantage is, so we have now this virtual frame, and we can place it wherever we want. And we do this during training. And because we now can simulate all the motions we want, this greatly reduces motion biases that you usually have in your data set. Now let's have a look at the architecture. So we use a encoder-decoder type network. As input, we have now the virtual frame and the current camera frame, and we have two decoder branches. So the first one computes the pose update. We decided here to have multiple pose hypotheses as output. This means we generate a large number of poses and then average them. We found that this greatly improves the accuracy about 10%. And to make sure that these predicted poses are not all the same, we train this with an uncertainty loss to make sure that they are properly distributed. The second branch predicts optical flow. We use this as an auxiliary task to help the network to develop motion features that are useful for this task. As you know, if you know the motion between the frames, this is very helpful for computing the pose. And we do not need this branch during test time because we're not interested in optical flow, so we can just turn it off during testing and save computation time. Now let's have a look at one result on one of the sequences of the Munich RGB-D benchmark. So here in green you see the ground truth pose, and in red our predicted trajectory. And as you can see, even after many frames, they are still quite close together. As depth, we use here the depth from the sensor, and the setting is pure visual odometry. So there's no post-graph optimization or loop closing here. Okay, let's come now to the mapping part, and the details will be explained by Huizhong.
Yeah, let's continue with the mapping part. So now we have multiple images, and we also know the corresponding camera poses. How do we compute the depth for the keyframe? Yeah, of course, we want to use the measurements from multiple images because we want it to generalize well. And on the other hand, we also want to exploit the image prior in the single image. And to this end, we use an encoder-decoder network that uses the keyframe image and also the measurements from multiple images as input and outputs a depth map for the keyframe. So the measurements is collected in the photoconsistency and cost volume. And the well-known problem of cost volume is that its accuracy is very limited by the number of depth labels. And to solve this problem, we use a cost-to-find strategy along the depth label axis. So we first use a regular spaced set of 32 depth labels, which we call fixed band. And after we have some rough estimate, we use a narrow band, where we compute the cost volume around the previous prediction. And this reduces the search range and allows us to capture more details with the same amount of depth labels. So this cost-to-find strategy maps to our architecture like this. We have two stages, a fixed band module and a narrow band module. Now let's take a look at the fixed band module. Here we just gave a rough estimate of the depth. And based on this estimation, we use the narrow band module, and the depth is extracted as a soft classification task. And the second component of the narrow band is that we append a refinement network after it, which adds explicitly a regularization to the depth map using only single image priors. And these two together can be seen as solving the data term and the regularization term alternatingly. And we can also apply this to run the narrowband module iteratively. So here is a result showing the effect of the number of iterations on the narrowband estimates. And you can see that with more and more iterations, it will give you more details. With this two-stage architecture, actually we can obtain a very accurate and detailed depth map. As you can see here, that you get the individual stone on the ground, and also the vertical stairs shape is well reconstructed. So we have already seen the mapping and tracking. And as we said, here we present a learned incremental tracking system, tracking and mapping system. And I mean, we definitely want to combine the advantage of deep learning and classic approaches. And by doing this, we can achieve a very accurate and robust system, and which also generalizes very well. Okay, thank you for listening. Please visit us at Poster afterwards.
All right, there are time for some questions, so please come forward to the microphone.
Over there.
Yeah.
Hi, thanks for the nice work, it's very great. I have a question about the optic flow module you have. I think I observed this in another work which is called like DeepTAM, which is also use optic flow network as a backbone to estimate motion. I think it's a great observation that like both yours and theirs works very well. But I'm curious that, I mean, what's the observation over there? Like if you use optic flow as that it helps you to generalize. And then there's another question, which is I think if you have optic flow, if you at inference time, you can do the prediction, and it gives you dense correspondence. And actually from the traditional method, you don't need to do any learning ConvNets about the pose. You can directly, if you only have image, you can estimate the like fundamental metrics, or if you have depth, you can directly do the regression using like correspondence. So what is like the choices of this, and how does it affect when you're doing your experiments? Yeah.
Mm-hmm. So first we observed optical flow really helps a lot. So I think the improvement here was about 20%. But you're right, of course, if you have perfect optical flow correspondences, there's no need for learning anymore. But in our case, so the optical flow is really not that accurate. It's really just an auxiliary task to help improve the post-prediction. Sorry.
So actually in this slide, you can see a comparison. Yeah. So this is without optic flow, and this is ours. So actually you can see that there is like 10 or 20% of improvement. So this optic flow really helps.
Okay, thank you.
Okay, let's thank the speakers again.